Vector is one of the simplest topics that we have in physics. Normally students, whenever they hear the word vectors and scalar quantities, most times always become afraid of the topic as if it is a very difficult task. So in today's class, I'll be explaining to you all you need to know about vectors so that anytime you see any question related to vector and scalar quantities, you'll be able to attend to it properly. I still remain your anchor, Mr. Ken. If you are new to this channel, please kindly subscribe, and you all can also click on the notification bell to know when I upload a new video. Thank you. Without wasting much of our time, let's get started. Alright, coming to this now, we have this to be our vector quantity. And under vector quantity now, we are going to today's class, we'll be talking about scalars and vector quantities. Then by the end of this class, students will be able to define scalar quantity, define vector quantity, give an example of each quantities, and also resolve vectors of any kind. So basically, this is what we'll be talking about in today's class. So without wasting time, let's dive into them here. Okay, so the first thing I need you to understand is, I need you to understand one thing. Let me go back a little bit. I need you to understand one thing. Coming to all these things they have written so far now, before I start explaining what scalar quantity is or what vector quantity is all about, let's start with the word quantity. When you talk about quantity, what do you mean by the word quantity? Now, when you talk about quantity in physics, it just simply means what? Quantity is scientific what? Scientific parameter, or quantities are scientific parameters that can be measured. So let me use the proper word. Let's say quantities are what? Are scientific parameters that can be measured. You may not properly understand how I mean by this now, but let me just bring it let me bring it down to a layman's understanding. Now, for you to understand it properly, the what they are trying to refer in this what quantity is all about is the names we call things, anything we measure, or the things that are measurable. The names we call them in physics, that is what we call quantities, or what they can also refer to scientific parameter. Now, let me take an example now. If you are to measure the elementary entities in a body, anytime you're measuring elementary entities in a body, you call that mass, and that mass is known as a quantity. So you call that quantity mass. So whenever you are like you call them, you call it mass. So whenever you are trying to measure interval at which events occur, it's a quantity. It's being measured. So that thing you call it, or what do we call it? We call it time. Now, whenever you are trying to measure 2 points apart, whenever you are trying to talk about 2 points apart, whenever you measure them and you are talking about 2 points apart, we call it what? We call it length, and so on. So you now see that in physics, those quantities, or any quantity that is being measured, or sorry, I mean that in physics we are referring that quantities are what? Scientific parameters that can be what? They can be measured. So these are the names we call things in physics or sciences that can be as what? That can be measured. So without wasting much time now, let's explain what scalar and vector quantities are all about. So let's start with the first one called scalar quantity. So what do we mean by scalar quantity? Now for scalar quantity, the first one, for scalar quantities, sorry, scalar quantities. Scalar quantities are those quantities. Scalar quantities are those quantities with what? With magnitude. It is either you call it magnitude or you call it size, or you can just call it numerical value. They only have numerical value, and no direction. So it means that anytime you call that quantity, Anytime you call that quantity, you're only going to call their numerical value, and you're not going to call anything about their direction. Now, please let me warn against one thing. For you to differentiate, I forgot to say it at the beginning, but let me just say it now. For you to differentiate one quantity from another quantity, what do we normally use now? We use what you call SI unit. We use SI unit to differentiate a quantity from another. Now, the reason why we use SI unit to differentiate them or to identify them is because all quantity will always have number or size or magnitude. And since they will have number or size or magnitude now, to differentiate a parameter from another parameter now, we use what you call the SI unit to differentiate that. So let's say if I say something like 2 Newton like this now, I can also say something like 2 kilogram like this now. I can also something like 2 seconds like this now. Each of them has number and they have the same number. But what differentiated this quantity from this quantity is the SI unit. So this one is referred to as force, and this one is referred to as what mass. So what will differentiate a quantity from another quantity, in as much as they will have the same, they might have the same magnitude or the same size or the same numerical value. What will differentiate a quantity from another quantity is the SI unit. So the SI unit is the only thing that you are going to use to identify the quantity that has that value, that value. So the SI unit is the only thing that you're going to use to identify the quantity. So what quantity is this now? You say the quantity is force. What quantity is this one? You say that the quantity is mass. And what quantity is this one? You say that the quantity is what? Time. Remember that anytime you see any alphabet that you see after a number, that alphabet is called the SI unit. That is, after a number, you see another alphabet behind it. It's called the SI unit. But whenever you see this alphabet whenever you see it in a formula, not after a number, it's going to be part of the formula. So that's the only thing I need you to take note of. So coming to this scalar quantity now, this scalar quantity will only have what you call numerical value. So which means they can be like this and no direction. And whenever I talk about direction, this is what I mean by the direction of a thing. This is direction. It is either we have north, we have south, we have north, we have south, we have east, we have west. So it's, and then we also have the one that can go from here to here. Maybe from here to here, it's going to be north, east, and then we can also have the one that goes from here to here, which is southeast. That is from here to here, it's southeast. Then we can also have the one that goes from here to here. This one is called southwest. And we can also have the one that goes from here to here. That is from here to here. This one is called northwest. So you now see that whenever you talk about direction, the quantity must face a particular side, either to the north or to the south or to the east or to the west or to the northeast and so on. So it depends on that. But when the body is not facing any direction, it simply means that, or if the body has no direction, it has no direction that it is facing, it simply means that that quantity belongs to the parameter or the family of scalar quantities. So let's see further example about this now. So let's say we have examples of scalar quantities. Now let's look at the examples of scalar quantities. I don't know why I keep spelling this as this. Example of scalar quantities. Now, what are the examples of scalar quantities that we have? Now, examples, the scalar quantities that we have the following as the examples. Now, I would like you to take note of all this. If I'm explaining this or giving examples of each of them, bring out your writing material, please, and be writing out each of them. Now, the examples that we have is, the examples are, we have speed as one of them. Now, you know that speed is just distance over time. So, and it's not in a specified direction. So it has no, whenever you talk about speed, it has no direction. So we also have examples like distance as part of it. We have distance. We have height as part of it. Then we also have length. We have length. We also have width. We also have altitude. Altitude. We also have mass. Another example is mass. Take note of all this. We also have mass because whenever you talk about mass, elementary entities in a body and whatever that makes up a body does not have direction. Space apart, that's what we call distance, and space apart, 2 points apart, is what we call distance, and it does not have a specified direction. How high something is does not have direction. Length, the same thing as distance. Width, the same thing as width, distance. Altitude, the same thing as height. So you now see that all these that I just mentioned now, they have no direction. So we also have some quantities like work, or energy. Work or energy. Energy is the ability to do work. Okay. So we also have distance. Sorry, we also have a density. I mean density. We also have density. Then we also have flux linkage. Flux linkage. We also have flux linkage. Then that is when you talk about the flux linkage, I'm talking about the number of lines. Number of lines. So we also have electric current. Another example is what we call electric current. Electric current, electric current or charge, or charge. We have electric potential, electric potential, electric potential, electric potential, which is in your V, or we also that is or your EMF. Then we also have pressure, pressure, which is your pressure is your force over area. We also have pressure. Then we also have a resistance, resistance. We also have resistance. We also have a capacitance, resistance. We also have capacitance. These are the examples of scalar quantities that we have. And inductance, inductance, inductance. Then we also have reactance and impedance. Reactance, reactance, and impedance. Impedance. Okay. Then we also have a mechanical advantage and velocity ratio. We also have mechanical advantage and velocity ratio. We also have efficiency. We also have efficiency. So these are the examples of what we call the scalar quantities. So I've listed out the scalar quantities that we have so far, and these are the scalar quantities. Though it can be more than this, so you can study more and get more examples and add up to what I have here now. So, but these are basically the ones you'll be seeing in your exam. That's why I said, if I'm explaining all these things, bring out your writing materials and be writing. The more you write, the more you understand and the more you remember. So, take your time, play this video again and again to remember all I said. Let's go over to the next one called the vector quantities. Let's go over to what we call the vector quantities. Vector quantities. Let's talk about vector quantities. Vector quantities. Now, coming to vector quantities now. What do you mean by vector quantities now? These are quantities. These are quantities with magnitude. If I do not call it magnitude, I can also call it size. I can also call it numerical value. Numerical value. And direction. Someone might be wondering, what's the essence of all these things we are learning? Well, it's just for you to know them. Now, the reason is because one of them is this now. You will understand by the time I start teaching you how to resolve vectors, you understand where there is a why if there is tug of war. Assuming we have tug of war, probably we have two persons here now. We have the guys, males, they are here drawing the rope. Then we also have the females. We have the females here. These are the females. They are drawing the rope. At the end of the day, we want to find out which of the following or which group will draw the other to the other side. Probably you have a line dividing them now. Probably on the process of dragging it, one of them, maybe the females drag the male towards their side, or the male drag the females towards their side. You know, like I said before, this one has to do with what you call, this is what you call a vector quantity. This is what you call a vector quantity, because by the time you apply that force, this group of people are pulling towards this direction. This group of people are pulling towards this direction, pulling, which is under the family of force. So pull is under the family of force. So which means that vector. So which means that force, as an example, is a vector quantity. Why? Because it has a direction. It's either you pull, you push, or you do other sort of things as well. So when you come to this now, vector quantities are very important. We have a lot of things to learn in under vector quantities. They have to do with what you call direction. And for you to represent that now, the direction might be either to the east, to the west, to the north, to the southwest, and so on. That is why anything that has to do with vector, you must show us the sign. That's why you must indicate that with the sign. Assuming you have F1, you can tell us F1 like this. You can give us something like F1 like this to show that this F1 is a vector quantity. Or even if you have it in the diagram, you must represent that. Let me just give an example of vector quantities that we have before I explain further about these vector quantities. Now, the examples of vector quantities that we have are, we have examples of vector quantities. Examples, we have the following examples as displacement. Distance in a specified direction is called displacement. We have displacement. Then we also have velocity. We have velocity. Then we also have weight. We have weight. Weight always pull the weight is that pulls the body down. Let's say this is the body now, and that force that pull the body downward is called weight. And the formula is always m times g. Weight is a form of force, because when you come to force, we have various forms of force that we have. And what are the various forms of force that we have? Let me give you an example of some of them now. We have a lot of them. We have something like drag as part of it. We have something like frictional force. We have something like frictional force. Then we also have something like gravitational force, gravitational force, gravitational force. What again do we have now? We also have something like tension, tension. Then we also have something like thrust. We also have something like thrust. We also have something like thrust. So when you talk about this now, all of them are in the same category. So I can just say weight or force. Weight or force, they are the same thing. So like I gave an example. Example of them, we have drag, we have push, we have pull. But let's put it easy. We have frictional force, frictional force. We have a gravitational force, gravitational force, gravitational force, gravitational force. We have magnetic force. We have magnetic force. We also have electric force. Electric force. Electric force. We also have tension under this. We have tension. We have thrust under this. All these things are just various forms of force that we have. So these are the things. So whenever you see any of these, you should bear it in mind that they are also under the category of vector quantities that we have. So the vector quantities that we have are not just weight and force. You should also bear in mind that we also have drag, frictional force, gravitational force, magnetic force, electric force, tension, thrust, and so on. All right, other examples that I can give to you under vector is, let me give you examples like, we have something like moment. We also have something like moment or torque. We have something like moment or torque. Then we also have what we call the field intensity or strength. We also have what we call the field intensity or strength. Field intensity, intensity, field intensity or strength. Field intensity or strength. And under this field intensity now, we have various form of it now. We have what we call the electric field intensity. So you should bear it in mind that I just called field intensity. You should bear it in mind that we also, under this, we have electric field intensity, electric field intensity. Then apart from electric field intensity, that's, I'm trying to list out those of them under this category of field intensity. We also have what we call magnetic field intensity. Magnetic field intensity. Then we also have what we call gravitational field intensity. So these are the things that we have under the field intensity. Remember, I gave examples of those of them under the category of force. I gave examples of those of them under force. So I've given out the field intensity that we have. Then we also have another example called magnetic induction. We also have magnetic induction. Magnetic induction as one of the example of vector quantities that we have. Magnetic induction and magnetic induction. Then we also have what you call magnetic flux. We also have what you call magnetic flux, magnetic magnetic flux, magnetic flux. Then we also have what you call um, electric current density. We also have what you call electric current density, electric electric current density. Then we also have, let me um, create more space. We also have what you call the stress, tensile stress. Okay, let's just call it stress. We also have what you call the stress as an example of vector quantity that we have. We also have what you call momentum. Momentum. You know, this momentum has to do with what you call mass times velocity. When you have two bodies and one has a higher mass than the other one, so what happened now? And both of them are set at the same speed. It's possible that when both of them collide, the one with higher mass will possibly take or pull down or pushes the one with lesser mass to the direction, to its direction. That is why anytime there is race going on, it's not expected that someone will cross the race track. Reason, because those people that are running they have mass and they are going on at a particular speed. So if you mistakenly block their way and if they hit you, you know what is going to happen to you. So you know that. So we have that is under momentum. So but momentum, we're going to explain that in full with time. Now we also have an example known as another example of a vector as field. And under this field, you should bear in mind what field am I talking about. I am talking about electric field as one of the examples. As one of the example, I am talking about magnetic field as one of the magnetic field as one of the example. I'm talking about a gravitational field, gravitational field as an example, gravitational field as an example of this. Then we also have the last one known as what? The impulse. So these are the examples of what we call the vector quantities. So I'd like you to take note of all these that I said and write them out. Know them very well because you're basically going to be seeing them in your exams and you need to understand what they are. Okay, so the next thing we're going to talk about is what you call resolution of vectors. Resolution. Okay, resolution of what? Of vectors. So that's the next thing we're going to talk about. So the next I'm going to be talking about is what you call the resolution of what? Vectors. So for this now, I would like to define, I will explain to you what is called the resultant vector. And I'm going to talk about what you call the equilibrium vector. And before I talk about that now, before I talk about resolution of vectors now, how do we represent vectors now? Vectors, whenever you want to talk about vectors now, how do you represent vectors now? Whenever you have your vector, you must represent your vector using an arrow. So which means it shows the direction it's going. So this is going this direction. Let's say I have this as my F1. This my F1 is going towards this direction, towards the east. What if I have something like this? This also shows the direction. This is F2. So you now see that for you to represent your vector now, we must have it this way. You must have a direction. You must show a direction or show direction. Now, coming to this again, I need to know one thing. One thing you need to know is that what if we have so many vectors? Please, when I say vector, please, what do I mean by vector? That vector could be, it could be, this place I said, resolution of vectors. It can be resolution of momentum. Momentum is an example of momentum is an example of vector. It could be resolution of impulse. It's not the most they will use the word vector. Vectors are many. It could also be resolution of displacement, resolution of weight, resolution of force, resolution of any of those, resolution of field. It could be any of these examples that I gave under vector. So the word vector, I am referring to any of these quantity, any of them. I'm referring to any of them. It could be impulse, it could be field, it could be momentum, it could be stress, it could be magnetic induction, it could be magnetic flux, moment, torque, velocity. So I don't want you to be surprised to come to the exam when they ask you resolve this velocity. You might be asking yourself, which one is resolve velocity? What you are taught is how to resolve vector. Please, they are the same thing. There is no difference. Sure, you get. So there is no difference in that. Just bear it in mind. So I might be using any of this word. I can use vector, I can use force, I can use weight. Just bear it in mind, but just bear it in mind that I can use any of those words. And if I use any of those words, I'm still referring to the same thing. So here that I use the word vectors, I'm supposed to be using the word here forces because actually I'm using two forces, force one and force two. But let me not bother myself with those words. Let me just focus on the word vectors first, since I've explained to you and I've notified you for you to know that whether I use the word vector or I use the word force, I'm still referring to the same thing. All right. So assuming we have two vectors, or we have two forces, or we have two weights, or we have two mass, sorry, not mass, two momentum, and so on. Assuming you have two or more of it now, and you expected to get a single force out of this, this is what you call. It is known as what you call resultant. This is what you call the resultant. We call it the resultant. It's either you call a resultant what vector, resultant vector, or resultant force, resultant anything that you want to call it that is under the category of vector. So how do we do that now? Resolution of vectors now. Remember, please, this place I have resolution of vectors. I'm also referring to method of calculation of vector. I can also let me just use the word method of calculation of vectors. So method of calculation of vector, that's what I'm referring to. So resolution of vector. So whenever you're giving more than one vector, how do you get a single vector? And that is what you call resultant vector. So resultant vector in the sense that you are expected to get a single vector whenever you have more than two or more vectors. You have to give us a single vector. So that's exactly what we mean by that now. So you should bear in mind one thing now. Resultant vector or resultant. Let me explain what resultant is all about. Resultant or resultant vector, resultant vector is a single, is a single vector, is a single vector that produces, that produces, that produces the same, the same, okay, let me, the same effect, effect as, as a as a set of vectors acting together. At a point. at a point. So that's exactly what we call the resultant vectors. So when you talk about resultant vectors now, it just simply means that we need a single vector. Just get a single vector. Get a single vector. We just needed to get a single vector. So just no matter how many vectors they are, no matter the number of forces they are, we just needed to produce a single vector or a single force. So assuming I have something like this, and I have something like this, this is just an analogy. I might not be correct. So I have something like this, and I have this, and this is my F1, and this is my F2, and probably this is my F3, F3, F3. Be careful. I have the F1. There is a direction here, so this is a vector. Now I have F2. I have an arrow here again. This is another vector. Then I have F3. This is another arrow. This is another vector. Here is going to be maybe I call this one F4. Why did I call this one F4 now? Let's look at this. I have an arrow on this line. So yes, which means that I have a vector here. That's what it means. So out of all these vectors now, I have four vectors or four forces. I'm expected to give a single vector or a single force, and that is known as what? Resultant what? Vector. So out of these four, I need a single force that will have that will produce the same effect as a set of vectors, and that is known as what you call what? Resultant vector. So how do we get a resultant vector? I am going to explain to you how to get a resultant vector when we have multiple vectors or multiple forces or whatever. So whenever we have multiple of it and you want to get a single vector or a single force or a single displacement or single whatever that belongs to the category of vector, how do you do that now? I'm going to explain that soon so that you understand how to do that. But before I explain that now, there's one other key thing that you need to take note of. And that which you need to take note of is what you call the equilibrants. I would like you to take note of what you call the equilibrants. What do we call the equilibrants? I would like you to take note of the equilibrium, the word equilibrants. Equilibrants. Now, what do you mean by the equilibrant now? Or the equilibrant was? Now, is a single vector is a single vector capable of balancing capable of balancing capable of balancing a given system of vector, a given system of vectors. So I'm trying to make you understand that this resultant is kind of opposite. Assuming this equilibrium is kind of opposite. Assuming this is our resultant and our resultant is going this way, it simply means that our equilibrium will go the other way. So if this is our resultant, equilibrium will go the other way, will go the opposite direction so as to balance it. So, but with time, we are going to be seeing each of them. I'm going to give an example so that you understand each of them properly. So, but for now, just bear this in mind that we have now. All right, so the next thing we need to talk about is how do we actually resolve these vectors? So that is exactly what we need to talk about now. Now, the method of calculating, so remember I'm talking about method of calculating vectors or the method of a resulting vectors. So method of calculating vectors there. So we have methods of calculating vectors depend depend on whether whether the vector the vector a straight line is a straight line or at an angle or at an at an angle at an angle to each other to each other. Someone may be wondering, what is this person trying to explain? Now, this is what I'm trying to say. What I'm trying to say is that for you to resolve this vector now, you need to take note of one thing now. How do you resolve them if they are just straight lines? They are just straight lines. This is the first one, and this is the second one. They are just straight lines. straight lines that are either straight line or they are in parallel, because when I'll start explaining, I'll give you that as straight lines or in a parallel line. So whenever they are in straight line, how do you resolve them? What if they are at an angle, either at an angle 90 degree to each other? We have this one, we have this one, or they are inclined to a particular angle, probably this angle like this. We have something like this. We have this one, we have this one, or we have something like this. What if they are like this? What if they are like this now? How do we resolve them now? That is exactly what I mean. That method of calculating vectors depend on whether the vector is a straight line, something like this, or at an angle to each other, something like this. So I will show you how to calculate each of them, how to resolve each of them. It's very simple. It's not difficult. So I would like you to be taking note of this, as I explained before. Take your time, don't give up yet. I mean, take your time, pause the video, and do. So just take some break and come back and continue from where you stopped. So let's continue from where we stopped. I am going to talk about now how to resolve vectors that are not just that are in straight line, like this one that we have here. Now, how do you resolve them since they are in straight line? So that is what I'm going to be talking about next. Then after that, I'll be talking about if they are inclined or if they are at a particular angle, either at a angle 90 degree or any other angle, say this kind of angle. So I'll explain to you how to do that. So let's start from the first one so far. So I'm going to be talking about vectors in a straight straight line or parallel lines. Parallel lines. Someone might be wondering, all these things we are doing now, what actually are we going to be doing with them? Now, let me just, before I give an example of what I mean by that now, assume this is a truck, and we have a force, someone is pushing it, you're pushing this truck now, you're pushing this truck this direction now. This is a V-box, let's say, okay, let me not call it a truck, let me call it a car, and you're pushing it, automatically the car is not moving, the tire is not moving. What if you have another person that joined you? Both of you are in straight line, both of you the same thing, they are just pushing it the same direction. So what happened now? It's possible that the car is going to move. What if you guys are like three? It's possible that the car will move. Then what if someone else stands in front, or there are some group of people that stand in front to push back? What do you think is going to happen now? You see, it's possible that this vehicle or this car is going to move only in the direction of those of them, or where it has the greater force. But for the first one that I said now, if you have first force, second force, and third force, let's say these ones are not here, you see that for this car to, when you were pushing it alone, the car wasn't moving. Someone added, someone else came and joined. The car seemed to move, and maybe you guys are not three, the car start moving. So that means that, assuming that your force, that your own force was 10, and the second force of the second person, or the force of the second person is 30, and the force of the third one is 20 newton. If you add it up, like one, if you add them up, 2, 3, and this is going to be about 60 newton. The car started moving when it was 60 newton, for instance, but when it was only 10 newton, it wasn't moving. So you now see that if the force or the vectors are going in the same direction, what do we do if they are in the same direction now? We add them up. So the first thing we're going to talk about is vectors in straight line. Number one, we're going to I'm going to start from what we call vectors in the same direction. So vectors in straight line, let's just say in same direction. If they are moving in the same direction, what are we going to do if they are moving in the same direction? So if they are moving in the same direction, what are we expected to do now? We expected to do what? Add them. Two forces acting in the same direction are being added. So what we have, two forces acting in the same direction. What do we do to them when they are acting in the same direction now? We add them. are being added. They are being added. So the forces are being added. The forces are being what? Added. So you add if they are going in the same direction. So let's say I have the first force as 100 Newton and I have the second force as 80 Newton. So the resultant force, let's say this is my F1 and this is my F2. So if I'm to get my resultant force, now my resultant or the single force that is going to have the same effect, total effect on this, I'm going to say my resultant is going to be F1 plus F2. So which is going to be what now? 100 plus 80. So which is equals what? What is it going to give you? It's going to give you 180 Newton. So I have 180 Newton because they are going the same direction. So you should bear it in mind that anytime forces or vectors are going in the same direction, we add them. Before I continue with that now, okay, let me just give another, let's go over to the second one first before I say what I want to say now, probably at the end. So now what if the forces are going in different direction? That is when you talk about the tug of war. So different direction. Okay, let's say they are going in different direction. So let's say the forces are going in different direction. The first one is going this way and the second one is going this way. Say the first one is about 100 Newton and the second one is about 80 Newton. This is your F2 and this is your F1. So what is going to be the resultant now? So if they are going in different direction, you do what? You subtract. So anytime they are going in different direction, you are going to subtract. So my resultant is going to be what? F1 minus F2. Please let me warn you against one thing now. Assuming this one is F2 and this one is F1 and I'm asked to get a resultant now, what will I say? Should I say resultant is equal to be F1 minus F2, where I know that my F1 is 80 Newton and my F2 is 100 Newton? No, I won't. Rather, I am going to say F2 minus F1. Why? I'm going to subtract the smaller one from the bigger one. So actually, I'm going to have 100 minus 80 and not 80 minus 100 to give you a negative sign. So you are not expected to get a negative sign from this now. So you are going to use the greater one. You are going to subtract the smaller from the greater one. That is exactly what you're going to do. So from what we have here now, I'm going to have it as 100 minus 80. So which is equals what? Equals what now? Equals 20 Newton. But there's one thing that I forgot to say initially. And what was that now? You should bear it in mind that anytime you get your magnitude or whenever you get your magnitude, because one feature of vector is that any vector or vectors do have what you call magnitude and what you call what now? Direction. This is the magnitude. This is the magnitude. So this is the value that it has. But how about the direction? So I need to talk about the direction, so which is what I'm going to comment on. Now, when you subtract this now, the direction of this is going to be what? 20 Newton towards, is going to be what? Towards the 100 Newton. And why did I say towards the 100 Newton? I'm just showing the direction. That 100 minus 80 is going to give you 20 Newton, which is the resultant. Then the direction is going to be what? This is the resultant is going to be 20 Newton. Then the direction is going to be what? Direction is going to be what? It is what? 20 Newton towards 20 Newton towards 100 Newton force. 100 Newton what? Force. So why did I say 20 Newton towards the 100 Newton force? Because 100 is greater than 80. So when we did 100 minus 80, we got 20. So this extra 20 is going to be going towards the higher force or the higher vector. So that is it. So towards the 100 Newton force, or yes, 100 Newton force, or towards the left, either one. So it must have direction. So it means that the first one that I taught you, whereby I have something like this, I have two forces. Okay, let's say, no, not this diagram. The first one I taught you, whereby I have force 1 and I have force 2, and then I have 100 Newton and I have 80 Newton. and I'm to get my resultant, I will just say my resultant is equals F1 plus F2. I sum them up because they are going in the same direction. So and I got 180 Newton. Now, what is the direction? If I'm to ask, or if I'm to get the direction, it's going to be what? Towards the east, because this direction is towards the east, towards the east, towards the east. So I can just say 180 Newton towards the east, towards the east. Then this one can also, you can just say 20 Newton towards the west. Yes, I can just say 20 Newton towards the west instead of me using 100 Newton force. It's also okay, but I can just say towards the west, which is 100 Newton force, which is towards the 100 Newton force. Sorry. So you should bear it in mind that aside you getting the magnitude, aside you getting the resultant, you should also bear it in mind that you might be asked to get the direction. And I've basically showed you how to get the direction for forces that are in straight line or in parallel direction. So whether they are in straight line like this or they are parallel like this, you should bear it in mind, you should know how to get their direction. Same direction you add, and whenever you add it now, it's going to move towards the direction of towards their direction. Like this, from here to here is towards the east. Assuming if it is going backward, it's going to be towards the west. If it is going upward, it's going to be towards the north, and if it is going downward, it's going to be towards the south. So that is exactly what you need to know, and nothing much. So before then, I'm going to talk about the next one, which is vectors at an angle. But before I talk about vectors at an angle now, okay, let me just talk about vectors at an angle. Remember that one of the examples of these that you need to know in a real life is when you have tug of war. Remember, I've given that example before. This is tug of war. We have the guys, they are pulling, pull. Then we have about, let's just say we have about let's say three guys here. We have about three guys. These are three guys. Then maybe we have about three ladies as well. Three ladies. Normally we have three ladies about here. Sorry for the diagram. We have about three ladies here. Then we have about three guys here. And probably when they were doing the tug of war, when you talk about tug of war, this force is going like this, and this force is going like this. This is for the Fm for the male, and Fw for the force of the female women, and the force of the men. So if they are going this direction now who among them are going to pull the other over their side? So let's just say during the process, and maybe the women won. They drag the men. Maybe these men are skinny enough. They not get weight. Like they don't have enough weight in them. They don't have enough mass. So they were able to drag them. So it simply means that these people might be producing a force of like say 100 Newton, and these people are producing a force of about 80 Newton. The people that are going to win are people that produces more force than the other partner. So let's just say these people are producing 80 and the women are producing 100 Newton. What happened now? Automatically, they will drag all of them towards their direction. So that is why I keep saying that it's going to be what? If you want to get the resultant or the net force or the resultant force, you just quickly say 100 minus 80 to get your resultant or your net force. Then the direction is going to be what now? Man, you draw all the men towards your direction, towards the direction of the women. That is why I say 20 Newton towards the west or towards the 100 Newton force. That was why I gave that example. I'm explaining this in this way because of those people that might be thinking that all these things that we're saying, does it really have an application? Yes, it does. It matters a lot in real life. So that was why I have to give this example. Okay, so let's go over to the next one. So, and the second one I'm going to be talking about is what you call vectors. Let's talk about what you call vectors at an angle. At an angle. Now, basically, I'm going to be talking about three angles at an angle to each other. To each other. Basically, I'm going to be mentioning three angles here now. It's going to be angle 90-degree, acute angle between the range of 0 degree to 0 degree to how many degree now? 0 degree to 90 degree between this. So 0 to 90 degree between 0 to 90. So I also talk about how to solve those of them between that is the obtuse. So those of them between what now 90 to what you call what now 180 degree. So that is what whenever we have those vectors, even I need to talk about those of them at a point, at a point, at a point, at a point. Yes, that's the next one I'm going to talk about 360 degree. So when we have too many forces at a point, so how do we solve them now? So these are the four things that I'll be talking about in vectors at an angle to each other. That's what I'll be talking about now. So I'm going to start from the first one that we have angles at whenever we have two forces at angle 90 degree. Then after mentioning, so I'm going to be talking about, okay, so under this I'll be talking about two forces, two forces acting perpendicular, two forces acting perpendicular, perpendicular to each other, perpendicular to what? To each other, to each other. Then the next one I'm going to be talking about is what we call more than two forces acting at a point. I'll be talking about more than two forces acting at a point. So the next one I'm going to be talking about is angles between two acting forces is acute. Angle between two forces is acute, acute or obtuse, or obtuse. This is where I'm going to take my time more and explain a lot of things that you need to know. So I'm going to be talking about these three things. Actually, it's actually four because this is one, this is two, and acting at acute, this is three, and this is the last one, which is four, and that reflects to what I've said here. So I'm going to start from the first one, known as forces acting perpendicular to each other, perpendicular to each other. So that's the first thing I'm going to talk about. So remember that all these things that I normally call forces, remember they are also called vectors. So this place that I called two forces, okay, I'm supposed to put S here. This place I mentioned as two forces, I can also call it two vectors. I can also say two displacement. Remember that I said that at the beginning of this class. So don't forget any of those things. So let's go back to the first one. Let's start with the first one. The first one says two forces acting perpendicular to each other. So that's number the first one is two forces perpendicular to each other. How do we resolve that? Then we have two forces acting perpendicular to each other, acting perpendicular to each other, to each other. Whenever you hear the word perpendicular, what do you mean by the word perpendicular? It just simply means that both forces are at angle what? 90 degree. So that is exactly what we mean by perpendicular. So let's just say this is the first force, this is the first force, and let's look at the second force. And the angle between both forces is how many degree now? 90 degree. So the angle between both of them is 90 degree. So that's what I mean by what? Perpendicular. So let's say this one is my F1 and this is my F2. But there's one challenge that you're going to be having whenever you see them in the exam. What challenge are you going to be having, or will you have when you see them in the exam? Now, when you look at these two forces now, these two forces perpendicular to each other can be categorized in two ways. First one, the forces are acting in different directions. And the second one, the forces might be acting in what? The same direction. If they're acting in the same different direction now, how will you draw the resultant? Yes, I am not talking about how to solve them yet. First thing I'm going to explain to you now is how to sketch them, how to sketch it first. Then after sketching it now, we'll now talk about how to solve it and what method do we use to solve it. That's the next thing I'm going to talk about. So the first thing I'm going to be talking about is it can be parallel to each other. Sorry, I didn't mean parallel to each other. How I mean is this now. The forces can be going in the same direction for perpendicular. For the perpendicular, the forces can be going in the same direction or in opposite direction. So let's say this one is in opposite. The forces are going in opposite direction, opposite direction, opposite direction for this one that I have here. And why did I say that the forces are going in opposite direction? So the forces are going in opposite direction. Now this is the first one, it's going this way, and this is first two, it's going the other way. Sometimes you can also have this in exam. I'm only trying to show you the different ways we're going to see it. Sometimes you can also have this. Now this is your first one, and this is going to be your first two. Remember, the reason why I'm mentioning this to be my first one and this to be my first two, or the reason why I'm calling this one vector one or first one or any form of vector is because there must be an arrow. If there is no arrow, you now know that this is not a vector. This is not a vector. It can be just ordinary number there or ordinary quantity there. So that it must have arrow. So this is first one. This is first one. Okay, this one. Oh, I made a mistake. Sorry. I meant something like this. Say I have this. So this is your first one. This is your first one. And then let's just say this is your first two. So you now see what is the observation now. This one is a what? Same direction. Same direction. You see that forces that we have here are going in the same direction in as much as the two forces are at angle 90 degrees to each other. These two forces are going in the same direction. And what direction are they going in? A clockwise direction. Then coming to this one, they are going in what? In different direction. This one is going clockwise and this one is going counterclockwise or anti-clockwise. So you see that both of them are not going in the same direction. Now, if you want to sketch their resultant, how do you sketch their resultant? That is exactly what I want to show now. Now, for this one that are going in opposite direction, I would advise you that if you want to sketch it, complete it first. Complete it. If you want to sketch, and show the resultant force, which is the resultant line in terms of diagram. So what you're going to do is complete it first. This line and this line are the same thing. Then this line and this line are the same thing. That is, this force and this force are the same thing. So what you're going to do is that since you've already completed it now, which of them are you going to use now? It depends on the one you decide to use. You are going to draw a diagonal. You will draw a diagonal. You draw a diagonal depending on the one you want to use. So let me resketch this here. Let me resketch it here so that it will be clear. I'm having so many. So you have this is my F1 and this is my F2. So you complete it. Then you now sketch a diagonal. Then the question is, why did I sketch a diagonal this way? Why did I sketch this diagonal this way? Now the reason why I did that is because I know that this line and this line are the same thing. This line and this line are the same thing. Now since they are going in the same direction, they are now going in the same direction because when I introduce this one and when I introduce this line, you now see that this one, this line, for if I'm going this way, they are now going counterclockwise. Then if I'm going this way, they are going clockwise. So I can use any of the triangle. I can use any of the triangle to solve my question. So this is going to be my F2 and here is going to be my F1 and here still remains my F2. So since I've already known that both of them are not going in the same direction, I will now draw a line that will not join both of them. A line that will join both of them. So before I sketch a line that will join both of them, I will make sure that both of them are going in the same direction before I now draw the line. Let me repeat what I said. Let me repeat that again. Look at this carefully. Watch this carefully. I have this line. I have this line. I have F1 and I have F2. Before I will draw my diagonal, I will make sure that both forces are going in the same direction. This one is going this way and this one is going this way. So how do I make sure that both of them are going the same direction? I'll complete it. I'll complete my line. So when I complete my line, automatically I know that this is going to be my F1 because these are going to be parallel to each other. So they are the same thing. then automatically here is going to be my F2. So I am going to choose the one that have the same direction. You now see that F2 and F1 are now going in the same this direction. From here, it's moved and ended here. From here, F2 ended here and F1 continued and ended here. So I will need a line that I will join that will start from here and stop at the ending point. Remember, this is the starting point. F2 started here, and because they are going in the same direction, F2 started here and ended at the end of F1, and F1 started here and ended here. So you now see that for both F2 and F1, they started here and ended here. So I will now draw a line that will join both. I'll just draw a line here that will join both ends, both their starting point and their ending point. So assuming I have this now, this is their starting point and this is their what? Their ending point, and I can now call this my resultant. I can use double arrow to represent that. I can use double arrow to represent that also. So that is exactly what I have here. Even if you check the other way around, it's still the same thing. Okay, watch out this. Watch out this. You will now see that this is F1. It started here and ended here, and F2 started here and ended here. You see that this is the starting point and this is the ending point. So I can use this rectangle to solve my question, or I can use this rectangle, right angle triangle. Sorry, this not rectangle, sorry. I meant I can use this right angle triangle to solve my question. I can also use this my right angle triangle to solve my question. Either way, they are the same thing. Now, since they are going the same direction, did you remember what I told you that anytime forces are going in the same direction? What did I say? Remember? Tell me. Okay. I told you that anytime forces are going in the same direction, what do we do to the forces now? We are going to add the forces anytime they are going in the same direction. So since F2 and F1 are going in the same direction, so what do we do now? I'll just say F1 plus what? F2. I'll add both of them. I must add both of them if they are going the same direction. So, and if you look at this now, you discover that my resultant will now will be going towards where both of them ended, and it's opposite direction, because this is F1. Both of them are going counterclockwise, and this one is going clockwise. This resultant is going clockwise. So even if I go with that now, let me just explain this. I can just say minus my R all equal 0, but I don't really need to do that this way. Though there's another way I have to explain it, but I just want you to understand one thing. I can just say F1, F2 equals, this is going to be what now? R. You know, the reason why I place it this way is for you to understand one thing. F1 and F2 are going the same direction, then R is going in the opposite direction of F1 and F2. That's why I use minus, and I took it over to the next side. But basically, this is not what they are going to. This is just explaining the direction of the forces. This is not what you're going to see in the exam. What are you going to see in the exam now? If you are to solve this question in the exam, they will tell you that the only thing you are to use to solve this question, or to solve any vector like this, is to use of what now? Pythagoras. Okay, so that the use of Pythagoras theorem. So use your Pythagoras theorem, which says your hypotenuse squared is equals to what? Your opposite squared plus your what? Your adjacent what? Adjacent squared. So that is exactly what we expected to use. And since I've already drawn this diagram this way, what is going to be my hypotenuse? The longest side, I'll just say r squared is equals, what is going to be my opposite? You know, it's going to have an angle here. Since both of them started, this force is F1 and F2, they started here. It's going to have an angle here that will help us get our direction. So you now say that what is going to be my opposite? My opposite is going to be what? F1 squared. And what is going to be my adjacent? Since here is hypotenuse and here is already opposite, here is going to be what now? Adjacent. I'll just say plus F2 squared. So whereby my R is going to be what now? Square root of what? F1 squared plus what? F2 squared. So, but in some of the questions, or where we are going to be solving it further, they can call this your F1, because this F1 is your y-axis, known as the vertical component, and this one is your s-axis, known as your horizontal component. So some places you will see them mentioning the word vertical component and horizontal component. So which means it can also be said that your resultant is equal square roots of vertical component, which is your F1 vertical component squared, plus F2 squared, which is your horizontal component squared. Now, somebody might be wondering, since you've already explained different direction or opposite direction, how about same direction? What would you do? Well, same direction, you see, they are going the same direction. So automatically they started here and it ended here. So the resultant will be what? It will be like this. Okay, you sketch like this. And where was it going to be pointing? It's going to be pointing at the ending point, not at the starting point. This is the starting point of the force. This is the ending point of the force. So it's going to be pointing towards the ending point of the force. And or you can also make sure that your resultant is going in opposite direction of the two forces. Remember, force 2 and force 1 are going clockwise. Then you will now make this one to go what? Counterclockwise. So that is how to do that, your resultant. So you still use the same, you still apply the same formula here to solve the question concerning that. So you still apply the same formula here. There is no difference. You apply the same formula, whether it is opposite direction or same direction, they use the same formula. The only reason why I'm sketching this is for you to understand how to sketch it, or if it's been sketched, you will now know what next to do. If it is being sketched and you are asked to get the expression, you should get the expression there. How will you get it now? That is exactly what I was explaining here. This place is not about the formula. It's all about the expression. How do you write the expression? You may not understand what I mean, how I mean by expression. I think that's what I'm going to explain next. In the next slide now, I'm going to explain or show you how I mean by expression, so that when you see something like that in your exam, in your JAMB especially, you will not be afraid. You will know what to do, how to write the expression. But for coming to this now, here is all about the formula that we normally use to solve two forces acting perpendicular or at angle 90 degrees to each other. So the formula that we use here is what you call the Pythagoras that we use. And this is the formula for the Pythagoras, and we have something like this. So